So I told you I'm just going to give you one more example of a probability space, and this one is the most important. So you've almost certainly heard of it before, but let me explain it anyway. This is the normal distribution. And I'm going to write this as n mu sigma squared. Okay? Just as a symbolic representation of this normal distribution, mu we will see is the mean, that's the usual notation, and sigma squared is the variance, which is also the usual notation, right? Okay. So this is a continuous probability distribution. The space of possible results is the whole of the real line, so the variable can be anything from minus infinity to plus infinity. And the probability density, P of x, is defined as follows. So I'll define it and then I'll explain why. 1 over 2 pi sigma times the exponential of minus x minus mu squared over 2 sigma squared. So we can draw what this looks like. I plot a function of p. It's x. You see that the power in the exponent is always negative, right? Because it's minus and these things are squared. So the power in the exponent is always negative. That means that this term is always less than or equal to 1, and is equal to 1 when x is equal to mu. So when x is equal to mu, this thing is a maximum. So let's suppose that mu is somewhere here. And at this point, the distribution attains a maximum, and the value of that maximum is just the prefactor here. So the value here is 1 over 2 pi. Then you see that as x moves away from the mean, this thing grows, in other words, becomes more negative, and therefore the exponential decreases rapidly. So as we move away from the point mu, this distribution decreases rapidly, something like this. Also note that it's only dependent on x squared, so therefore it's got a perfect symmetry around the point mu. And the rate at which this distribution decays is governed by the parameter sigma squared, so therefore this width here is related to the value of sigma. So this is the normal distribution. Mu tells you where the center is. Sigma tells you how wide the distribution is. So I want to get some results for this normal distribution. The first thing is to really explain to you why is there this funny factor of square root 2 pi times sigma at the front. This is just to normalize this distribution. In other words, just to check that the integral over the whole of space of p of x dx, that's the total probability, should be equal to 1. So we need to check this. Integral from minus infinity to infinity, p of x dx. This is 1 over square root 2 pi times sigma times the integral from minus infinity to infinity of e to the minus x minus mu squared over 2 sigma squared dx. Okay, we can simplify this a good deal by defining a new variable, making a substitution. We say that y is equal to x minus mu divided by sigma, then you see this is nicely just y squared over 2 here. Okay, and also as a differential, dy is equal to dx over sigma, and dx over sigma is exactly what we've got here, dx over sigma, so that also goes away. So when we make the substitution of x into y, this becomes 1 over the square root of 2 pi, the integral from minus infinity to infinity, e to the minus y squared over 2 dy. Okay, so this is an integral you may not know how to do. There is a way to do it which I will show you at the end if there's time. But for now, I'll just state the result. The result is the following. If I integrate from minus infinity to infinity, e to the minus alpha y squared dy, then the result you get is equal to the square root of pi divided by alpha. This is true. I will prove it at the end if I've got time. If not, I'll probably do it next class. Okay, so in this case, alpha is a half, so this just gives me, okay, so let me call this result star, right? This one here, I'll call it star. And then if I use that result on this equation here, this is equal to square root of 1 over 2 pi times square root of pi over alpha, and alpha is half. And you see that this gives you 2 pi, so that everything cancels, and this gives you 1, as it should. So as long as you believe me about this result star, I get total probability equal to 1. Okay. So that's checking the total probability equal to 1. The next thing I'm going to do is calculate the mean and variance of this distribution. And as it's suggestive by the notation, we will find that mu is the mean and sigma squared is the variance. But we need to check. Right? So let's calculate the mean. So the mean is defined as the integral from minus infinity to infinity of x times p of x dx. This is 1 over square root 2 pi sigma, integral from minus infinity to infinity of x times e to the minus x minus mu squared over 2 sigma squared integral dx. Again, I'll use the same substitution as I did before. Y is equal to x minus mu over sigma. So this means that x is equal to y sigma plus mu. So here I get 1 over square root of 2 pi times the integral from minus infinity to infinity of y times sigma plus mu times e to the minus y squared over 2 dy. Okay, so that's a straightforward integral by substitution. The reason you do this is because this first term here must give you 0. This first term here must be equal to 0 by symmetry. Let me explain that. Well, the first function, this e to the minus y squared over 2, looks like this. It is symmetrical around the y-axis. Right? And here, y sigma is a function which looks like this. It is anti-symmetric. It's odd around the vertical axis. So when I integrate these two things, whatever I have on this side is exactly the negative of what I have on this side, so therefore the two things cancel each other out. So the integral from minus infinity to 0 is exactly equal to minus the integral from 0 to infinity. They cancel. Okay, so that's 0. So then I get now the integral 1 over square root of 2 pi, the integral from minus infinity to infinity of mu times e to the minus y squared over 2 dy. And then you notice that that integral I've written here is exactly the same as the one we saw earlier for just the probability distribution, except that it's multiplied by mu. Okay? The only difference between this integral and this integral is the presence of the mu here, right, which is a constant. This integral gives you 1, so therefore this integral must give you mu. Okay, so the result is that the mean is equal to mu. As I said, it must be. Okay, so finally, we'll calculate the variance and show that it's equal to sigma squared. Okay. And I'll use the initial definition of the variance we saw, which is that it's equal to the integral of x minus mu squared. Okay, that's definition of variance. So now if I put in what p is for the normal distribution, then this gives you 1 over square root 2 pi sigma integral from minus infinity to infinity x minus mu squared e to the minus x minus mu squared over 2 sigma squared dx. And again, we'll use this substitution y is x minus mu over sigma, which in this case gives you 1 over square root of 2 pi, the integral from minus infinity to infinity of y squared times e to the minus y squared over 2 integral dy. Okay, so there's a trick to evaluating integrals like this. If you've got y to the power n times e to the minus y squared times something, then there's a trick to calculate the value, so I'll show you that now. You write it as the following thing. This is equal to 1 over square root of 2 pi times the derivative d by d alpha of the integral from minus infinity to infinity of y squared e to the minus y squared over 2, e to the minus alpha y squared dy, set alpha equals a half. And then multiply by minus 2. Sorry. That's also gone. That's correct. Sorry. And this should be minus 1. Then I believe we're okay. Okay, so let me explain how we got from here to here. If I look at, let's check that it's the same. If I differentiate with respect to alpha in here, the alpha is here, right? So if I differentiate here, d by d alpha e to the minus alpha y squared is equal to minus y squared times e to the minus alpha y squared. That's straightforward, right? So you see that differentiating with respect to alpha brings down the y squared, which is what I want. Okay? So when I differentiate with respect to alpha, this will bring down a y squared. It also gives me a minus sign, which I don't want. So I multiply by minus 1 to get rid of the minus sign. Okay? And then finally, I have to say alpha equals to a half, because here it's alpha y squared. Here it's y squared over 2. Okay, the reason we write it in this way is because we know this result is over there, star, right? So by star, this is equal to minus 1 over 2 pi times d by d alpha of square root pi over alpha, set alpha equals to a half. Because I know what the result of this integral is. So this is alpha to the minus a half. So when I differentiate it, I get square root of pi times minus a half times alpha to the minus 3 halves. And I set alpha equal to half. Okay, so square root of pi's cancel nicely, so this minus is cancelled, so I get 1 over the square root of 2 times from here, times a half from there, times a half to the minus 3 halves. From there, and these all cancel, right? A half to the minus 1 cancels. This is a half to the power of half. This is a half to the minus half. So this all cancels. Okay, which is good, except I made a mistake, which is easy enough to correct. There's a mistake here. Okay, when I go from this line to this line, the first sigma is cancelled by the sigma here, but when I replace x minus mu with y, x minus mu is equal to sigma times y. So here I should have sigma squared. X minus mu squared is equal to sigma squared y squared. That's what was missing. So, I mean, that doesn't make much difference. It just multiplies everything by sigma squared here, and sigma squared here, sigma squared here, and sigma squared here. And this is important, as I said, because the powers of a half all cancel, so all you're left with is the sigma squared, which is the result I wanted. Okay, so that's the normal distribution. It has a mean equal to mu and a variance equal to sigma squared. I've proved that. If you don't like the calculation, then just remember that result. Okay, and its picture, it looks something like this. It's called a bell curve. It has it's symmetrical around the mean, and it decays exponentially at either side of the mean. And the width is proportional to sigma.